Welcome everyone. How are you doing? It's a very special occasion. It's one of my favorite lectures to give. I should actually call it Recursion and Chaos. I've actually made a copy for this one. Didn't think it was a few weeks since I last had a copy. So yeah, it's a lovely celebratory occasion for recursion. Great. Monday mornings. Okay, so first of all, I will say a few things about what we discussed last week, which was randomness. And the most important thing for us in the context of applying these algorithms is how do we control it? You remember the list that I had? I am deliberately not going to display it right now. Let's see if we can remember it. So what were the parameters that I could control in a random generative process? So the first one, which is very straightforward and kind of obvious, what do we control? The range of values. Okay, so typically we can say, let us have random values within a certain range from minimum to maximum. And then the interesting thing is that we can define the range in multiple ways. So we can say between minimum and maximum, but what we can also say is center and deviation. Okay, so this can be quite crucial. It gives you both approaches give you two parameters. One gives you minimum and the maximum. The other one gives you the center and the deviation. But the crucial thing here is that if you have a center and deviation, then the deviation actually acts as the amount of randomness. So if you pull down your deviation in the second scenario, then with your center value, you're actually plain controlling the parameter. And then you can add a bit of random, a lot of random, and so on. Whereas if you have a minimum and a maximum setting, then if you want, 3,000 with a little random, you have to push up the minimum and the maximum both to 3,000. And if you want 1,000 with a little random, you have to pull them both back down, right? So you actually don't have a separate control of randomness. You have the minimum and the maximum. So I guess you can imagine scenarios where either is more useful than the other one. So what I'm trying to highlight here is think about it in terms of your application, which one makes sense. Okay, so that was the range of values. Okay, what else? Someone said something with time. Did I hear that right? So obviously you can control the timing of it, the rate. Typically, the rate control has to do with the triggering mechanism. So when do you ask for the next random value? So it's not inherent in the random process. Okay, nevertheless, we kind of talked about it because it can be crucial in our applications. Okay, what is the next one, which has to do with the likelihood of outcomes? Distribution, exactly. So that one allows you to control which of the outcomes is more likely to occur. In essence, a balance of outcomes. Okay, so you can actually say, well, I want my open hi-hat to play 20% of the time. I want my closed hi-hat to play 80% of the time. Okay, so that is distribution control. Okay, and then there were two more, which are a bit more tricky and kind of interrelated as well. One of them I've dubbed pace, okay, which has to do with how quickly does the random generator move through the available range. Okay, so it is independent of the range. It would still have a fixed range in terms of minimum and maximum, but its speed in moving around can be different. Okay, so I'll briefly say something about the pace and the spectrum of noise. I believe I didn't get the time to talk much about that last time. So the interesting thing here is that if you have white noise is a set of totally random numbers. Maybe you know this already. If you have a digital audio file and you insert just purely what we call uniform distributed random numbers, which means that the distribution is uniform, there's no more likely, less likely, then you play that back, a pure 44,000 random numbers, you play that back, you get a second of white noise. Okay? So that, in my metaphorical domain, would equate with me appearing at random at any position in this room. Okay, because I'm totally free, I'm not constrained by my previous value, but by my previous position. Okay, the reason I talk about this metaphor of me randomly appearing in the room, well, one thing, it's fun to think about this. But the reason I do this is because I want to contrast it to the Brown noise, which has to do with me taking a random step from my current position. Okay, so you can imagine this is a slightly different scenario where I start walking randomly in the room, right? I won't just appear in that corner all of a sudden. And this is Brownian noise, and in Max MSP, this is our drunk generator. Okay, so you have been asking about, okay, so what's the difference between random and drunk? Well, the random will appear at any possible point at any time, whereas the drunk will always take a random step from the previous value, and in that, we can control what they call the maximum step size, right? So you can control how much I can leap every next step. Okay, so you kind of get the idea there. In terms of a process that you imagine to randomize, you can think of, okay, so what do I want? Do I want this thing to actually erratically jump back and forth? Or do I want it to walk? They also call the Brownian motion the random walk. Okay? And the most interesting thing is in between. So we have brown noise, we have white noise, so these also map into the audio domain. So that's the interest here. We're talking about generative algorithms spitting out numbers at control rate, making notes, whatever, hi-hats. And then we're linking this to the audio domain where you actually hear these noises and you see the spectrum. Okay, so white noise, you know, is technically flat. A brown noise has much more low frequencies. But the one in between that you might have encountered already is called pink noise, which has more low frequencies, less high frequencies, and it's halfway between the white and the brown noise. And in order to generate pink noise, you have to go through a bit more trouble. I have a very neat pink noise generating algorithm. If you're interested, I'll talk to you about it in the practical. I'll just mention that if you analyze most music in terms of, you know, MIDI notes, the composed music, not necessarily audio files, but if you analyze a sequence of values that represents MIDI notes, in terms of its spectrum, why wouldn't you be able to? You actually get a pink noise-ish spectrum. Okay? So what you actually get is that if you think about my metaphor of my random position in the room, if you have music, or a lecture for that matter, where I randomly appear at any point in the classroom, it is not quite musical. However, with music, if I always just keep walking from where I currently am, well, it does something, but it's very predictable. In music, we need a bit more jumpiness, but we need a bit more predictability than the pure random position. Okay? And that is something that has to do with why, potentially, we claim that most music has a pink noise pattern. And if you ask me about this algorithm in the practical called FOSS algorithm, you will see how it actually makes sure that there is some sense of randomness at multiple scales. And we'll talk about that briefly in a bit, because with recursion, which is today's topic, oh yeah, let's just finish the random stuff. Okay, so we had this space. Okay, so I had this whole idea, this whole talk about the spectrum of noise had to do with the phase, right? Because brown noise, white noise, and in between the pink noise. And then one last thing that I talked about in terms of random number generation had to do with Markov chains, was the control of the sequence, right? So you can actually create a random process, a generative process that has a certain amount of sequence control. And the way the Markov chains work is that they allowed you to specify what happens what is the likelihood of different things happening based on the previous values. And if you look at only one previous value, then it is a first order Markov chain. If you look at 2 previous values, 3 previous values. So the nice thing about Markov chains, for example, if you do a second order Markov chain on the written text, you get a kind of interesting gibberish. Because there is certain reproduction of rules. So typically, if you have a Markov chain in place, you will always have 2 words after each other, which were originally after each other in the sampled work. Okay? So with Markov chains, what you can actually do is you can do 2 things. One is you can specify the likelihoods of what comes next based on what was previous, which is a lot of likelihoods. These are typically tables of values. You can specify it by hand, but you can also analyze existing data to figure out what came after what and what was the likelihood of these sequences. And then you have a set of probabilities, these matrices of probabilities, which you can use to immediately generate data. So people have done this with written text. You stick in a book and you say, okay, now generate something similar. And obviously it doesn't make sense on a long scale, on a larger time scale, because, you know, a sentence after sentence, they don't really connect. Even within a sentence, you will get meaningless stuff. But actually, word by word, it kind of makes sense, because every word by word combination is a combination that already occurred. Okay? So, again, interesting stuff there, and something for you to explore. Okay, so that's about the random. So just to reiterate, range, we had a kind of rate control, which is not inherent, but definitely part of it. Then we had the distribution control, we had the pace, or the spectrum of the noise, and then we had the sequence. So these things kind of interconnect, interrelate, I should say, but from our perspective, they're quite distinct. So that's why we talk about them in that way. Okay, so we're coming to recursion slowly but surely, which is essentially something of, what should I say? It's just brilliant. When I figured out what it does, I was just mesmerized for days. I was like, wow, this is amazing. So for today, what we're going to do is talk briefly about difference equations, which you have seen, some of you, APDI people. Then we're going to talk about bifurcation to chaos. Yeah. And then orbits and attractors and a bit of fractals. So all those lovely terms that you might have heard before and unlikely in the context of generative music. So briefly about the terminology that I like to use. Random, we talked about this. The interesting thing is that it's supposed to be unpredictable. Okay, so again, the randomness is a perceptual term. At least I like to use it that way. Whereas if we talk technically about whether something is random, we talk about correlation. And actually correlation does go between 0 and 1. If you have one correlation, it means that the data is identical. If you have 0 correlation, it means that there is no similarity whatsoever. So we have a technical way of discussing this. So we keep the random, I keep the random for just discussing how we perceive something, whether something is random or not. So it is unpredictable. It's supposed to be non-deterministic, right? So there should not be a way of determining the next value, literally. Okay, so it is just totally unpredictable. And statistically defined. That's how we typically define randomness. So with distribution, if we say it's uniform distribution, it's white noise, then typically we assume that we know everything there is to know about such a process. Now, from last week, you remember that what computer gives us is pseudo-random, which is actually chaotic. Right? So now we get to the more detail of that process, because in a computer, in a digital computer, things are deterministic. Right? It doesn't ever make a mistake. If your computer does something weird, it's a programmer's mistake. The electrons don't go berserk. There is nothing that can go wrong with your computer, except that the programmer didn't take account of a possible set of input values and therefore the output value is something undetermined. But actually, in the core of it, the digital computing is fully deterministic. Okay, so therefore we cannot produce a really random value with a digital computer because it's supposed to be non-deterministic. However, we can produce a lot of interesting chaotic algorithms which are deterministic, however quite unpredictable, or at least depends on the one that you're using and depends on the scale that you're looking at and other things. Okay, so a chaotic algorithm can be unpredictable, but it is deterministic. So you can actually produce an equation that does it, right? There's nothing random about it. It is just unpredictable due to the nature of the equation. And chaotic stuff is generatively defined. So we don't necessarily define it by looking at the big picture. What is the statistical property of this data set? We actually say, well, this is the algorithm that produces it, and then we think we know all there is to know about such a process. Okay? So those are crucially different things. And then two more terms. First of all, iterative. Some people use iterative for recursive. I like to separate these terms. So I use iterative for strictly defining repetition, looping, right? For loop, you do something many times and done with. That's what iterative is. It has also to do with industrial production. That's my little metaphor there. Because if you look at, I don't know, your phone or those bottles of water, actually they're quite identical. So what we have is a blueprint, and then we create instances, right? So that has, again, to do with object-oriented programming, for those of you who study that, in the sense that you have a prototype, you have a class, and then you have an instance. Okay? So that's iteration. Now, recursion is slightly different from that. It is a process that relies on repeating the same step all over again, but the crucial thing is that the output becomes its input. That's horrible. I should say the input becomes its output. See, that's me getting confused with the lovely feedback. Okay, so that's the point in a recursive process, that you don't have a blueprint and then repeat instances, keep producing instances, but you actually have self-replication. So when you multiply laptops and bottles of water, you're doing looping, but when you make kids, which is potentially more fun, you do self-replication, right? Because two people make the next human being, and that next human being is able to make the next one. Okay? So hopefully one day we'll have industrial processes that are inspired by this, and you can actually, you know, have two laptops, leave them for a night, and then in a few days you get a little baby laptop. Okay? So at least we can do this with algorithms. Okay? So cross-pollination is a term, believe it or not, in the area of evolutionary computing. So we do produce algorithms that kind of rely on this model of evolutionary development rather than the model of iterative industrial development. Okay? So again, that's this magic about recursion, that once you create a feedback loop, once you stick the output into the input and potentially get confused like I did, then things really start happening. So for those of you who have been to the Noise Lab sessions, that's what we've done. We've actually taken two mixers, some stupid old pedals, and we made sure we had a lot of feedback loops. And what happened is just totally unexpected, rich, crazy, noisy, rhythmical, pulsating, beeping, and screaming stuff. Okay? So that's the fun thing when you get the feedback. Now, for you, I mean, if you haven't been to those Noise Lab sessions, you might have to wait for the next year because those ones are finished now. However, there is evidence of what went on SoundCloud, so you can look that up. But for most of you, I reckon for now, feedback is that one thing you want to avoid when you have someone on stage. Okay, because then it gets into howling. Okay, so that's a feedback where you only have a growth factor which is larger than 1. I'll talk about growth factors in a bit. And it's typically boring. So in order to get really nice things from the feedback, well, first of all, we have to have gain in the feedback loop, such that the thing starts doing stuff on its own. But then you have to have a nonlinearity, and typically an inverting nonlinearity. And once you have that, then things start to get chaotic. And this happens in control domain, which is something we're going to look at. But it also happens in audio. The term to, if you want to look up music, which relies on this principle, you have to look for no input mixing, no input mixer. Okay, so that's what they do. Mixer allows them to create feedback loops, and there is no input. There is no sound source in the whole thing. It's just a mixer and effects. And that's what we've done in the noise lab. Okay, so that's the intro. And now we're going to look into some detail here. Okay, so first of all, difference equations. What they are equations that tell you what is the difference between the output value and the input value. The reason I said you might have seen this is because we define filters like this as well. I won't go into this. Finite impulse response filters are actually feed-forward structures. Okay? And infinite impulse response filters are feedback structures. So actually that's why they're a bit less stable. In drawing up your difference equations, typically you use y to note the output value. You use the index to note which one. So n is typically the current. So when you see yn, you read it as current output value. Okay? When you see x, then you read it the input value. The reason why there's no x's in here, because these are all recursive equations, recursive difference equations, meaning that the output value is defined by the previous output value. So you see, I don't have an input value in this equation. The only thing I'm defining is how the next output depends on the previous output. So you cannot uniquely create the set of data which is a unique output of this, because the input value is not given. So typically, if you have a recursive equation, you would have the first input value, which is something we've discussed it last week in the random lecture. Random generators have a value which they start off from, which we call seed. Okay, so a seed value is necessary for all of these equations to get started, because all they do is, in this case, this one says the current output value is the previous output value times 0.9. Okay, so you've seen this patch already, and what it did is it created an exponential decay. Right, so if I start this equation with the seed 1, the next value will be 0.9, the next one 0.81, the next one 0.72, and so on. And that produces a neat little exponential decay. And for those of you into signal processing, that is actually an infinite impulse response filter, a low-pass filter. Okay? So really interesting when these things connect. I mean, it's kind of a high-level thing. So I guess if you're thinking about such stuff for your final year project, I'll be happy to help you unravel these beautiful mysteries. So that's a simple one. I rely only on the previous output value, and I multiply it with a fixed value. Okay, another recursive equation here, what you see is the Fibonacci series. You might have seen this one before. It will produce a kind of a spiraling in 2 dimensions, or it will produce kind of escape to infinity. Escape to infinity is a term. We'll talk about this in a second. And this one is defined by saying the current output value is the sum of the 2 previous output values. Right? So typically you start the sequence with 0 and 1, and then the next one is 1 again, because 0 plus 1, then it's 2, then it's 3, and then it's 5, and then it's 8, and 13, and 21, and so on and so forth. So you get obviously a set of values that really quickly adds up and starts going into very large values. Fibonacci series. And then the interesting thing is, what you have is that the golden ratio is being approximated by this Fibonacci series. So the ratio of 2 numbers will actually tend to converge, that is the term, to this value called the golden ratio. Okay, and then the one that we're going to look at today, it is the simplest thing that actually creates chaos in one dimension. And what it does, it says the current output value will be the previous output value times A, and the previous value 1 minus the previous value. Actually, I'm not quite sure. Maybe I've made a mistake here. I think this is n minus 1. So you're looking just at the previous value, and you're using it twice. So on one side, you multiply it. That's what we call the growing of it. This is the growth factor, A. And on the other side, you're limiting it. You see, it is inverting. This is your inverting nonlinearity. And if you stick this into a feedback loop, then things start to get wild. Okay, so let's look at this logistic map. Here it's right, so it's n minus 1 in the second one as well. I'm not going to code it for the time constraints. Don't say this when you're submitting code. But I'm going to show it to you as a working plugin in Ableton. Ableton Max for Live, obviously. So here it is. Let's first look at the patch. So it is actually fairly simple. What I'm doing here is I'm taking a MIDI note in. So typically when I produce these Max for Live generative plugins, by the way, there is about 50, 60 of these online on maxforlive.com, a fairly large set of bits. So I take a note in and I use that as my clock. Okay? So typically these plugins don't have an internal clock because I might want to clock them in any possible way. And if I do this by inputting a note, then in my sequence I can create a rhythmical clock. It doesn't have to be a steady pulsation either. Okay? So most of these plugins, if you start to explore them, what you will understand is that they're made to be flexible, they're made to be modular. So typically one of these doesn't do much, but if you start assembling them in MIDI effect racks, then you get the opportunity to make really powerful generative stuff. Okay, so the clock here is the input node, and then what happens, everything that happens really is this little feedback loop. So essentially what I'm saying with the float object is give me the previous value. That's the thing that's happening here. So, and then there is one equation, which is the equation that you've just seen. So what I have is here $F1 is the left-hand side input value, and $F2 is the right-hand side one. Okay? So the F1, the float 1 here, is the input value coming in. And then what I'm doing is I'm multiplying it with the growth factor, which I call the coefficient right there, and multiply that with 1 minus that incoming value. So we have the growth factor and we have the inverting nonlinearity, and that does it, believe it or not. Okay? So what you have here then is that value goes into the float, which is a kind of a memory cell, and waits for the next bank to be output, and then the next calculation, which depends on that output value. You see, that's how you recycle the output values. The output value becomes the input value. That is the crucial thing. That is the feedback loop. So once you do that, then for each clock that comes in, which is currently just an incoming node, you will get the next value from the algorithm, and that's it. Here you already have the output of the logistic map. And then what I do here is I scale it and offset it just for it make it useful. Typically these values, raw values, will go up to, well, what is it, I think about 2 or 3, something like this. We will see it in a second. And then if I want MIDI nodes, which is what I'm getting to at this stage, I have to scale it up because I want values up to 127. And also I offset it because I might want a small range of pitches, large range of pitches, up or down. So this is just my little admin in terms of making this useful, but everything there is to this logistic map is exactly the equation. Growth factor, inverting nonlinearity, and the feedback loop. Okay? And obviously the seed is there as well, because we have to start it off with a value anyhow. Okay, so what does a logistic map do? Well, it all depends on the growth factor. So the growth factor in recursive processes is really crucial. And by the way, part of this science is very closely connected to evolutionary biology. And the reason is that these processes can model certain species in terms of their numbers year by year. Okay? So what the link here is that in biology, what you have a growth factor, which is how horny the species is, right? And then you have the limitation factor, which could be many things. It could be the amount of food, it could be a predator population, it could be anything. And typically what you have, if the growth factor is small, you will have a stable output, which means that year by year you have a similar amount of units or what is it, animals, more likely. And then if you have a slightly larger growth factor, you get into oscillation. So one year there is just too much offspring, and then the limitation kicks in hard, the virus comes, and then they really reduce significantly for next year, but the year after, again, there's many of them. So I think some mosquitoes are like this, bugs. I really don't know evolutionary biology that well. But typically you have this oscillation in terms of numbers. And then, if the growth factor is really large, then you get chaos, right? So you don't get this kind of bump against the limitation and then down again and then bump and down and bump and down, a kind of an oscillation, but you get a total chaos, okay? So that's where it arises, the chaos. It arises from the moment when you get a large growth factor. So let us explore this. I'll close this, and if everything is right, I have a little thing playing here. Okay, so what I currently have, I'll make it a bit higher pitch. Okay, so this is my plugin. Okay, I'll make it also a bit faster so we get a better idea of what's happening. Okay, so what you hear here is a kind of a 4 cycle. Yeah? So the nice thing about these algorithms is that, first of all, if the coefficient, the growth factor is sufficiently low, you get a stable output. And then if the growth factor is increased, the output rises, and then at some point you get an oscillation. So here I have a 2-cycle oscillation, up and down. Still 2-cycle, growing, span. Still growing the range, 2-cycle. Growing. Okay, I'm starting to get a 4-cycle thing. And then things start going really quickly. Okay, and that's when it broke. Okay, so this is what you have. So we can look at this sequence of values in terms of what we call the bifurcation plot. And this is what you've just heard. Okay, so what I had is an increasing growth factor. Actually, this is the growth factor. That's the output value. So actually, it terminates at 1. I was wrong saying 3 or 4. And then as the growth factor increases, what I'm plotting here is all the output values, right? So this is not your typical XY graph. Here what I do is with this growth factor, I keep running the algorithm and all the values land just there. Okay? So a single point that relates to a growth factor means that in that case, a single value is being output. By the way, what happens, what I didn't show you really, is that if I started off from a different seed, which is then the current output value, then it kind of converges to that value, right? And the nice thing about these algorithms is I can start it from any possible value. If the growth factor is fixed, it will always converge to that exact value. Okay? So I'm increasing the growth factor, and then at one point I get the bifurcation. So it splits in two. And then in this range of growth factor values, what I had is a 2-point oscillation. 2 values in sequence. And as I increase the growth factor in that range, you've heard that the distance of those 2 values was growing. Yeah? And then at one point, I suddenly get a 4-value oscillation, this range here. Then I get an 8-value oscillation, then I get a 16, and so on, and then it bursts into chaos. Then you can't really predict what's going to happen anymore. You can define it generatively, you can say something about it statistically, but it's not really worth it. What you do is you get the chaos, and then the most interesting things happen, that at this point here, you get a 3-point oscillation. So you see that actually here things get really dense, okay, and there are these gaps in chaos in which you get these odd number oscillations as well. It's a really, really rich thing there. And you've heard that it actually has something musical. I mean, it was the most stupid possible example. You were just hearing the notes, the chaotic notes, but it gave you a sense of there is something behind it. There is a process behind it, right? It wasn't just random values. Now, the random generation, the pseudo-random, actually uses this kind of chaos, and it uses a point where it is really unpredictable. Okay? And then what happened after is it blew up. The whole process blew up. Okay, so maybe that's what's awaiting humanity as well, if our growth factor, overgrows. So you also kind of sense that, there is an oscillation, okay, and then after that comes chaos, and after chaos comes the blow up. So that's typical of these recursive systems. Cool. Well, I think that is the crux of it in terms of excitement and interest. I have a few more things. Here is spelling out of it. So what are the growth factors? So you have convergence towards 0, then you have convergence towards a fixed point. These are the terms we use. Then you have periodic alterations, between two values, what we call a 2-member limit cycle. Obviously, if you dig into chaos theory, you will encounter these terms. And then we get the next bifurcation at 3.449499. We get 4-member cycle, 1816, and then we get chaos. So, few more terms, if you dig into this, can be useful. Obviously, we don't really have an exam in this. This is the kind of interesting stuff. So convergence. You've seen convergence towards a stable value, but we also have convergence towards what we call a strange attractor. Okay? So I'm going to show you a few strange attractors in a second. And it means, convergence means that the algorithm is kind of getting somewhere. And it could never get there, as in with the strange attractors, and it could actually get there, as in it has a point that it approaches and reaches. Okay? Periodic motion That's fairly straightforward, you understand this one, and then a slightly more elaborate definition of chaos. So I've added into this that it's non-periodic, okay? Complex motion that gives rise strange or chaotic attractors. We'll talk about these attractors in a second. Now, the term that we use frequently to describe these data outputs is orbit. Okay, so typically this also works in astronomy. I don't know if you're aware of the three-body problem that Newton realized is a problem. So we kind of think that the world is easy to predict, and obviously we have good evidence in terms of creating all these gadgets. But actually, if you have three bodies that have a gravitational pull, you already cannot predict what's going to happen after a certain amount of time. So, because essentially it's a recursive thing, right? Because the next set of positions depend on the previous set of positions. There is a little equation in there, but the thing is, it's a recursion, right? So depending on these parameters, if there is a growth factor, if there is a nonlinearity, then it is likely to go into chaos at some point. But even if it doesn't, what you have is that there is a long-term unpredictability. So these recursive processes are sometimes described by the butterfly effect, which came from meteorology, because weather patterns are similarly recursive and therefore long-term unpredictable. So they can fairly accurately tell me when the rain is going to start in the next few hours, but in terms of next week, they can't really predict it very well. So the predictability of recursive processes is questionable, especially long-term. And the butterfly effect covers the idea that because these processes depend on really little variation, what we call the starting value sensitivity, a butterfly wing flap in, I think, South America could cause a storm in Europe. That's the idea, because you never really know which little detail, threshold, crossing of a threshold, will actually become responsible for a huge sweeping effect. Okay? And that again has to do with the fact that it's a recursive process, and every little thing, every little bit can actually become the avalanche trigger. And it's a funny thing because it seemingly the culture operates along those lines as well. You don't know whether next year it's going to be yellow or blue umbrellas. And that's why what we also have is that the startup business model is so successful, because what you do is you make 1 million of umbrellas of each possible color, and then for some reason everyone starts buying the yellow umbrellas, and you make enough money to cover all those unsold umbrellas, right? Same thing, you just invest into 100 things a bit, because one of those investments will produce an avalanche effect, instead of saying, oh, well, I'm going to invest really big into these 2 things that are likely to, produce an effect, but maybe they don't, and then you've lost it all, right? So that, again, has something to do with how recursive processes function. Okay, so those are the orbits. Here is a little bit of background in terms of nonlinear dynamics. If you want to read up on serious science behind this, please do. High sensitivity to initial conditions, that's what I've just described. And then, many natural phenomena can be better described like this: atmosphere, solar system, plate tectonics. There's a list of those things. So it is really overarching. So we've looked at a one-dimensional map called the logistic map, which is the simplest case. Here is a similarly simple but two-dimensional case, and this is already what they call a strange attractor. So in this case we have 2 equations, because there is x and y. It's a two-dimensional map. You run those 2 equations, and the orbit starts looking like this. So one run, you get a point here, you get a point here, you get a point here, point there, point, point, point. And your points keep filling in this form without ever making it a complete solid line, which is what it seems to be in this graphics. But actually, it's infinitely perforated thing. And the funny thing about these strange attractors is that a point will never overlap a previous point. So you start getting more and more points, more points. They all seem to be attracted by this shape, but there is never a repetition in values. Okay? Which is great, which is mind-boggling. Obviously, if you feel inclined to code it, it's not that difficult. So have a look. And then a few more terms, just so I kind of make the perspective complete. You probably heard the term fractal. So a fractal is a similarly generatively defined shape. Typically it's a bit bold, but I think I say infinite detail. Because you are generatively defining it. So you don't say, well, actually, I'm going to run this recursion 1,000,000 times. You define it as the recursion. So if you run it infinite times, you will get infinite detail, I guess. And typically what they produce is self-similarity, okay? Which is something that has to do with patterns on different scales, at different scales. So in nature, one of the things that's really nice and self-similar is broccoli. Okay, so the shape of the whole broccoli is actually the shape of a little bunch of, like one section of the crown. Do you call it a crown? And then if you look into the detail of that one little bit there, it's actually the shape of the whole thing and the intermediate shape as well. So fractals are quite present in nature. Actually, the solid geometric forms are present due to humans. Everything else is a bit of a fractal, okay? Because the nature does not do design. We design it. We say, let's have it a plane. The nature has growth, right? So if you define something like a broccoli, you are better off defining it as how does it grow, and then you get all these shapes growing out of it, rather than saying, well, this is the overall shape, this is the outcome, right? So the nature does not deal with the outcome first. It has a growth pattern. Okay? And then the funny thing is we also have a fractal dimension. So most of these things can be defined as having a fractional dimension. And typically you can describe shapes, natural shapes, by a non-integer dimension. Okay, so here comes to mind the coastline. So if I ask you what is the length of British coastline, the right answer is it depends on the scale that you're looking at. Okay, if I look at the large scale and I go like, okay, that's about few thousand miles. But then if I look into more detail, oh, wait a minute, there is a bay there, there is a little peak there, whatever, you look into more detail, then the coastline length becomes longer. And if I look into really the utmost detail, if I look into every pebble on the beach, right, I look into more detail, it's more rugged, and I get 1,000,000 miles or more. Okay? So the length of this coastline depends on the scale that you're looking at, and that's typical for fractal shapes. And then fractal dimension is a way of defining the amount of detail, so to speak, in this shape without saying, okay, well, that is the length of the coastline at this zoom level. But you have a way of talking about the ruggedness of this coastline without expressing its length. Okay, and that's fractal dimension. And then to finish off, I have just a few ways of creating fractals. So we have iterated function systems. Okay, so we have a fixed geometric replacement rules like Koch curves. We have escape time fractals. I'm going to show you the Mandelbrot set, which is this. And we also have a random fractal where you kind of do something random to the algorithm as well. So finally, this is a beautiful escape time fractal that you might have seen before. This is what we call a Mandelbrot set. And that is the equation, believe it or not. Z here stands for a complex number, so it has an X and a Y component. And the only thing it does, it says the next value is the square of the previous value plus a constant value. And that's it. Okay? So it's a very simple equation, you could say. And how does it create such a shape? Well, it creates it. This is not an orbit. What you've seen with Hannon's attractor was an orbit, so the actual output values. this is an escape time fractal. So in order to generate this picture, which is, by the way, infinitely zoomable and self-similar, right? So you have this shape, and then that shape repeats here, and in here that whole shape repeats, and on the edge of that it repeats again infinitely, okay? So the reason why we can do this infinite zoom is because we don't look at the output values, we actually have a grid of seeds, okay, so the starting values for the algorithm, and then we plot the escape time. And the escape time has to do with how long does it take before it goes off to infinity. And then the edge of this graph is actually a set of values which don't escape to infinity, which collapse, and a set of values which do escape to infinity. And then you can kind of do different colors or different shades based on how much time it takes for them to escape to infinity, right? So this is actually a plot which has to do with the grid of seeds, and then each point is defined by just running this seed through the algorithm forever and figuring out what happens there. And therefore you can zoom into it, right? Because if this is now, whatever, between -2 and +2, a kind of a grid, then I can go between -0.2 and +0.2, and I can go 0.003 to 0.004. So I can actually keep expanding it, I can keep zooming into it. And that's the funny thing, the mind-boggling thing, is that you can infinitely zoom into it and infinitely find, again, the exact same shape. Well, I shouldn't say exact, but the same shape recurring. Okay, so that's your escape time fractal. Cool, guys, that was a pleasure. Any questions, comments? Cool, thanks for coming, and then I'll see you soon.